Hey guys, we're going to go through your student notes in the Physics 10 student notes handout package thingy. Okay, here it is. So first, what is a wave? A wave is a repeating or periodic disturbance that transfers energy from one place to another, either through a vacuum or through a medium. And by medium, we're just talking about any matter. Okay, so the key point here is that waves transfer energy. Okay, so classifying waves. Let's talk first about mechanical waves. So mechanical waves are waves that travel through a medium. So that means air, water, earth, wood, fire. Haha, little joke there. You won't get it. So yeah, just any medium, could be anything, any matter, basically. Okay, so some examples of this are sound waves, waves on strings, water waves, seismic waves, etc. The list goes on. Okay, our next kind of waves are electromagnetic waves, and these do not require matter. So these will propagate then through a vacuum. Or space, if we're outside the most vacuum is in space, so that's what we're talking about. Propagate just means it is moving, and it continues, it keeps going. So the wave keeps going by itself. You don't have to add energy to the system. It just keeps going through space until it hits something, basically. All right, so examples here are visible light, infrared, ultraviolet, microwave, radio waves, gamma rays. We'll look at those in a little more detail later on in your packet, but basically these are just different wavelengths of electromagnetic radiation. All right, so here we have a transverse wave on a Slinky, and this is the classic example of that. The movement of the particles for a transverse wave is perpendicular to the direction of energy transfer. So what that means is if you pick a spot on your Slinky, like right here, what you're going to find is that one individual particle is just moving up and down, okay? Even as the energy is moving laterally. Okay, so the energy moves to the side, but the particle, an individual particle, just moves up and down. So that is a transverse wave, and this is the defining characteristic of a transverse wave. So then we come to longitudinal waves, and in a longitudinal wave, the movement of particles is parallel to the direction of energy transfer. So in this case, when we look at our particle, it is just going to move horizontally, and the direction of energy transfer is also horizontal. So some examples of transverse waves would be electromagnetic, water waves are transverse waves, obviously waves on slinkies or standing waves. Actually, I'm going to take standing waves off because they can be longitudinal as well. Classic example of longitudinal wave, probably the most important one, is sound. Okay, so, and we'll talk a little bit more about the characteristics of both of these here right now. Okay, you've been given this activity, and I'll try to hit the key points. Okay, so what happens when the frequency of the source is increased? A couple of things happen. The wavelength decreases and the period increases. Okay, sorry, both wavelength and period decrease. I need to learn to read. Okay, we increase the amplitude slider to 75%, and what happens? So wavelength and frequency are going to stay the same, but the wave height will increase. So what that tells us is that amplitude and wavelength and frequency are not related, okay? They do not affect each other. So imagine a small cork is placed in a tank. Try to describe the motion of the quark over time as the waves pass by. The quark is just going to bob up and down because these are transverse waves. Okay. All right. So frequency. These would be the number of waves passing through a given point in a given amount of time. Another way to think of frequency, because it's not only applicable to waves, you could think of it as the number of events over time as well. And so here's a possible equation for frequency, where frequency is equal to the number of events divided by a certain amount of time. Okay, the unit for frequency is an inverse second or a hertz. Okay, so whenever you're thinking about a hertz, you should be thinking inverse second. So 1 hertz is equal to 1 inverse second. There you go. Very important that you know that. Okay, so period. This is the amount of time required for one wave to pass a given point. Okay, so you just set an arbitrary point and then you measure the amount of time it takes for that wave to pass that point. And that is your period. Okay, period is related to frequency by this equation, and therefore this equation is extremely important. Our period, capital T, is equal to 1 divided by frequency, the inverse of frequency. Okay, and if that is true, then frequency must be the inverse period. Okay, so if you know one of these, you know the other one, and they are inversely proportionate, which we may come back to later. Okay, we're going to talk about some characteristics of waves. The first thing we need to think about is wavelength. So the wavelength is the distance between peaks or troughs of one wave. This definition is slightly problematic because it doesn't include longitudinal waves. So we could also say the distance between we could say rarefactions or compressions for longitudinal waves, and we'll see what that means momentarily. We have not defined those yet. So, generally what that means on a transverse wave is we're going to measure peak to peak. That's just the very top of the wave, or trough to trough. That's the very bottom of the wave. You could also measure other points on the wave, but it gets a little more difficult to do that. The most convenient place to do that, though, if you're going to measure the wavelength across another part of the wave, is the 0 to 0. You need to be a little careful there because if you measure the next 0, you're going to measure a half wavelength. Okay, so peak to peak and trough to trough are kind of the safest. All right, so amplitude is the maximum wave displacement as measured from the midpoint of the wave. Okay, so here I show maximum displacement. You could also draw it down here. That would be okay. And let me point out a really common mistake that you should not make. This is not amplitude, okay? This is double the amplitude, okay? So you need to be very careful not to just measure trough to peak, because that is going to give you twice the amplitude. And this is a common exam trick that people will use to trip up students, okay, particularly on like multiple choice questions. Okay, so next we are going to look at some graphs. So first one is a displacement position graph. So here we have displacement on the y-axis and we have distance on the x-axis. So we can look at our drawing here. Displacement, distance. Okay, so when we talk about distance, we're talking about a length of string, right? So if we look at a particle, we don't have a numbered axes on the x-axis, but we can imagine this particle here corresponding to this position, right? And this particle here would then correspond to this position. And this trough here would correspond to this position, okay? So that's what we're dealing with. Hopefully that makes sense. Okay, so we don't have time on this axis. I have labeled all of these characteristics. We have the resting or equilibrium position, and that is just going to be wherever the wave has a displacement of 0. And remember that this is going to be changing over time, but we cannot see time on this particular graph. So what we have here is a snapshot of our wave in time. So if you imagine just taking a picture of the wave and then graphing its displacement, and that's what we have here. So this graph is a photograph of a wave in time. Okay, so displacement has been marked. Amplitude is maximum displacement as given by 1 and -1. We have wavelength marked in 3 places here. We also have crests and troughs marked as well. The direction of wave energy propagation is actually a little bit problematic because we don't have time on this graph. So we can mark it here and that would make sense. But if we were just looking at our graph, because we don't have time on the graph or any other reference points, we don't really know the direction of energy propagation. But because we have this diagram here, we can tell if the hand is over on the left, then the direction of energy propagation must be toward the right. Okay, next we're going to look at what are called compressions and rarefactions. So here we have snapshots of a medium transmitting a longitudinal wave. And here I just had to assign a wave direction. We can't actually tell, again, from any of these graphs, which way the wave is going. Okay, so this is totally arbitrary, that wave direction there. So it says, annotate the diagrams to indicate compression, rarefaction, wavelength, and direction of wave travel. So our compressions are areas where we have high particle density or high pressure. So where you have lots and lots of particles, you are going to have compression. And a rarefaction is given by this low density area where you have very few molecules. Okay, so fairly straightforward. Note that if you look at the graph here, it's not really obvious where the compression and rarefaction is if we're just looking at the displacement graph. And in DP physics, we will analyze that a little bit more, but you basically need to consider the direction of particle travel. So in this case, our particles are traveling in this direction, and that's how we know that our compression is formed. And over on this side, our particles are traveling in the opposite direction. But it's not terribly intuitive. I wouldn't worry about it too much right now. Okay, our wavelength can be measured from compression to compression. Measuring from rarefaction to rarefaction is a bit more difficult, as you can imagine. So generally, when I am dealing with these, I always measure from compression to compression. Okay, so now we have a more traditional displacement versus time graph. And from this graph, we can get, excuse me, a bit more information. We note that we can get amplitude from either graph. It doesn't matter. Amplitude is going to be the same. But we're only asked to mark it on this one, so I've done that. So our period is given by the time required for one wave to travel to a certain point, or in this case, you can just find one entire wave and trace down to the x-axis, and that will give you t, your period, on the x-axis. Frequency we can't actually mark here because we don't have the inverse of time on an axis. Okay, so a little difficult to do that. I've marked amplitude. Okay, so here's some practice problems, and I don't think I need to explain all this because it's kind of a rehash of what we've already discussed, but if you need to pause the video now and take a look, please do that. Okay. So here we have wave 1 and wave 2, and you did need to calculate the period for wave 2. Note that it is 0.5 seconds, and I have marked off the 1 and 2 seconds here, but I have not marked off the smaller increments because I was in a hurry. Sorry for the poor drawing. I also noted that the scale on this graph is a bit off. Look at this distance here. These are not equal increments. I'm probably going to need to fix that at some point because I find it annoying. Okay, so for the next part, we're looking at two different graphs. One has displacement versus time, and the other one has displacement versus distance. And remember that these are two different graphs. Of the same wave though, okay? So we need to find wavelength, and for that we're going to look at the distance versus displacement graph. So that's graph 2, and we'll find their wavelength is equal to 0.3 centimeters. Again, we just trace out one whole wave. We could do it anywhere. I chose to do it from here to here. But you could have gone from here to here. That would make your life a bit more difficult. Or from here to here, again, making life a little bit more difficult. Starting at 0 is always a good idea. Okay, the period, we need to go up to the other graph. And again, we just trace off one complete wave, starting at 0. And we get 0.25 milliseconds. There we go. On graph 1. Okay, so for amplitude, we can use either graph, and we will find that it is 2 millimeters. Okay, not 4. Do not measure the whole wave from trough to peak. Okay, what factors affect the speed of the wave? The main factor is the material itself, but temperature may also affect it, and there are a few other factors in your book, so like spring constant, for example. But material, the material itself is the big one, and then probably temperature would be the next big one. All right, amplitude and period frequency do not affect wave velocity. They don't. It's a bit weird. So no matter how hard you punch water, it's not going to affect how fast the wave travels. It's a little bit non-intuitive. How is the wave speed equation derived? I've just shown the wave speed equation here. I was in a hurry at this point. Find the speed of a wave in a metal spring if a pulse travels 7.5 meters in 3 seconds. So we rearrange our wave equation slightly. Actually, this is our traditional one. Here we're just using distance divided by time. Okay, so what we find is our velocity is 2.5 meters per second. That's not right. That's what happens when you get in a hurry. Okay, next, what is the frequency of a 4.0 meter per second wave if in the distance between two successive wave crests is 0.25 meters? Plug in your values, you will get 16 hertz. Challenge, and here I'm just going to start going through these very rapidly. Number 3, the answer is 1.1 meter per second. And I will just put this up and you can take a screenshot or pause it. Okay, guys, that is it for your student notes, and have a great day.